So this is my final lecture on chapter 5, and the name of this lecture is the laser principle. And essentially what I will be speaking here is that I will be introducing to you the very first basics regarding lasing action, the laser principle, and how we can realize lasers. So I will be speaking about a little bit about absorption processes in a solid piece of a material. Then I will be speaking about stimulated emission, population densities associated with the electron states. And then, of course, I'll be speaking about thermal energies, thermal excitations, so a little bit about the stochastic nature of these processes. Then I will be saying how we can realize a condition known as a population inversion that enables us to actually realize stimulated emission as a dominant process. And then I will be speaking about at the end of the lecture about phase coherence of the stimulated emission and what is needed to realize a laser, so that it's not just enough to have a stimulated emission, but we actually also need other ingredients to actually make a light amplification device using stimulated emission. So this is the final lecture I have on this chapter, and what I will do here is that I will consider what we need and go through what we need to make a laser. And in terms of motivation, why we care is that this topic, of course, is extremely important because of the applications we have discovered as a mankind for lasers. So it's a really brilliant, nice light source that can be used to do lots of many things and interesting and important things. And this is the reason why we care. So unlike LEDs, incoherent sources of light, lasers are very bright, and this is the kind of difference that can be used in many of applications for the benefit of mankind. In terms of physics and math, of course, this topic also shows us that it's also the statistical nature of light matter interaction and the processes that take place inside the solid that are quite important to understand the whole mess of macroscopic light matter interaction. So it's really the statistical nature of those absorption and emission properties that we must understand in order to understand, for example, how a laser crystal behaves. Main processes or phenomena that we must understand like when to realize what's a laser. Of course, we need to understand absorption processes. So somehow we are pumping energy into our laser crystal, lasing medium, and then stimulated emission, we are somehow in a controllable manner extracting this energy or transforming this energy into a more useful form. So absorption, of course, as a process gives rise to losses, so that cannot be avoided. But on the other hand, absorption also allows us to store energy inside the laser crystal or lasing medium. It doesn't have to be crystal in principle. It could be also like a portion of a fiber or a waveguide where we have absorption and a gauge medium. And then we also have stimulated emission as a process, and this is the process that enables us to actually amplify light, incident radiation. So we, in a nutshell, we have absorption, and this is the process that allows us to store energy inside the laser crystal. And there are different ways how do we store energy, but it could also be done by shining light into the laser crystal. And then we have stimulated emission that helps us to extract this energy that we have stored in a way that we can actually amplify light that we wish to amplify. And thinking about the processes, absorption and stimulated emission, of course, like we must deal with probabilities. So we must deal both absorption probability and the probability for stimulated emission to take place. And what are the ingredients, what are the different things that matter when we want to calculate these probabilities? Well, of course, we want to understand what kind of population densities we have for the electrons for the system. So essentially, what are the state densities in I's? And then it is this term that tells us of how many electrons we have that are populating the state I, a given electronic state, excited state. And this population density is a very crucial parameter, and we can understand the dynamics of things by just knowing what's the population densities. In addition, the temperature of the system is often quite high. So with this high here, I mean roughly room temperature. And of course, maybe for us, that doesn't seem like a high temperature, but in terms of population dynamics, this is somewhat high of a temperature, because we already are working with energy regime where we can very easily excite electron states, atomic states into excited vibronic states, so that we can excite lattice vibrations in our solid piece of a material with the room temperature in place. And then because we do have the laser crystal and the device operating at this so-called high temperature, the population densities that are associated are also affected by thermal excitations. So we have thermal energy associated with the system, and here and there, every now and then, this thermal energy can excite the electronic state into a slightly higher vibrational state. And because this happens, we must take this into account when we are looking into the actual dynamics of things. And we want to calculate things that what are the probabilities, we must take this into account. So it's a dynamic, it's a statistical process that takes place. So the absorption and the emission processes, and because of that, we really need to take use of the tools that we have learned in statistical physics. Nothing strange here, just basically like a few simple equations and just a kind of general understanding that these are statistical processes in nature. So when we are in thermal equilibrium, what happens for the population densities? So that the population density for the first excited state, N1, and the population density for the second excited state, so N2. And these, of course, are the electron densities, how many electrons we have in these given states. These, in the thermal equilibrium, they follow the Boltzmann distribution. So this is one of the most fundamental laws or rules that we know from thermal physics and thermodynamics. So that we can calculate what are the population densities in N1 versus N2 by just equating them with an exponential that depends on the energy of thermal energy. So we have this kBT here. And depending on the temperature of our system, this guy tells us how populated the second excited state N2, or what is the population density N2 with respect to the population density of N1. So in other way of saying, depending on the ambient temperature of our system, like we may have a different population in the higher electronic state N2. So kBT is our thermal energy, and at room temperature, we're speaking roughly of 26 millielectron volts. And here, of course, the N1, like I said, is the population density associated with the state 1. Here, I'm labeling that to be the ground state, and N2 is the population density of the excited state. I think I have a figure coming up soon. Yes. So here I have my figure, and instead of G, I'm actually having 1 as the ground state here. And this Boltzmann distribution tells me how easily I can excite things if I'm just relying on thermal excitation. H is the Planck constant, Kb is the Boltzmann constant, and mu naught is the frequency corresponding to the energy difference between the states. So basically I could use a little bit less sloppy notation, and I could describe that frequency nu as a nu 1, 2, being more explicit that I'm actually speaking about the energy difference between the state 1 and state 2. And he, of course, is the temperature of my system. So here I'm basically, depending on how far they are apart, the two different states, I'm having a different number out of here. And of course here it's the temperature, the ambient temperature, that dictates how readily some of the time the electrons from the ground state are being excited into the second state. And depending on the temperature, we have more electrons on here, and depending, of course, on the energy difference, we may have more electrons in here. But since we are speaking about electronic transitions here, we are more interested in generation of light, that kind of electromagnetic radiation. The energy differences, nu 1, 2s, they correspond roughly on the order of a few electron volts. At room temperature, so that would be the 300 kelvins, the kBT value is 26 millielectron volts, like I said. And this, of course, is not much in terms of electronic excitation energies, so which are of the order of 1.6 to the 3 EVs. It is quite a bit considering the vibrational states of the system. So what this means is that when we have the medium of interest at room temperature, most of the electrons are in the ground state. So here in the ket of 1. And in this case, it's really the absorption that is the most probable process. Like we cannot really go lower than the ground state. So only thing that can happen is that the system will absorb photons and be excited into the higher states. So this is essentially what happens here at room temperature. But we want to amplify light, right? This is what the whole lecture is about. We somehow must break the condition of being at thermal equilibrium. And how do we do that is that we pump the system, and this essentially just means that we are bringing energy outside from the system into the system. And in figure, what we mean here is that we are pumping, we are shining light, or we could also electrically pump or thermally pump the system in principle, and we are raising electrons from the ground state into a higher state. So this is what we mean that we are pumping the system. We are bringing energy into the system from outside. Often one uses optical pumping, and essentially here we would have a strong source of light. For example, it could be a fiber laser oscillating or emitting at the green wavelengths, and this could be used to pump my laser crystal. Another way of pumping would be electronic pumping, and this is essentially done most of the time when we have semiconductor lasers. And here it's essentially an electric current that is being pushed through the piece of a semiconductor, and that enables to excite holes and electrons in the system into higher state, and this helps out to actually pump the system. So essentially we have a PN junction in the semiconductor, and we are driving an electric current through it, and it creates electron hole pairs, and these act now then as the gain medium of my semiconductor laser. Then it could also be the case that we would have thermal pumping, and I believe that this is being utilized in some gaseous systems. So basically we are taking use of the thermodynamics of gases. A helium neon laser would be a practical example here. That could be a little bit there. It's really the thermodynamics of gases and the thermal pumping that plays a role. So that the molecules are hitting each other, and because of this, some of the molecules are being excited into a higher electronic state or vibrational state, and this in essence acts as a pumping mechanism. In any case, whatever is the pumping mechanism, and here I'm highlighting optical pumping and the electronic pumping as the most important ones. Optical pumping you can do and use to make very high power lasers, but of course electronic pumping is energetically very much more cheaper, so that we can just have an electric current generating my pumping of my laser crystal. So unlike with optical pumping, you need to first somehow generate the light that is being used as the pump, so that it's not as energy efficient. But of course, in terms of making high power lasers, most of the time it's really the optical pumping that is the most dominant process that is being utilized. And what we want to achieve is that we want to somehow break the thermal equilibrium. So we want to somehow achieve a situation where the population density of the higher state, so the population density N2, is higher than the population density of the lower state N1 of the ground state. So essentially we must achieve this kind of condition so that the N2 would be greater than N1. And this condition is known as the population inversion. And this is something that we cannot realize at thermal equilibrium. So we must somehow break the thermal equilibrium by pumping the system. And of course, like we must pump it hard enough so that we can actually break the equilibrium condition. But the nice thing is that when population inversion takes place, so when it applies, so that this condition N2 is greater than N1, then stimulated emission can actually happen. And what that does then is that then it really relaxes the electrons from the state 2 into the ground state of 1. And it does so via stimulated emission, and that then acts as the key that we can actually amplify light. So that then instead of 1 photon, we can actually get now 2 photons that have the same properties as the portion of light we want to amplify. So incident photon stimulates the emission process. The electron is being relaxed and a photon is being emitted. And now the interesting thing here is that we have the incident and we have the emitted photon, and they have similar properties. And the interesting or the more important thing, or most important thing here, I would say that they have the phase coherence with respect to each other. And this is really the kind of key that distinguishes lasers from normal incoherent light sources such as LEDs. And here, since we are amplifying light, the medium starts acting as an optical amplifier. So this is now that we have realized in this kind of system. So we pump the system away from the thermal equilibrium, and then we actually have more states in here. This is what the condition here says, N2 is greater than N1. So we have more dots on the state 2 than on the state 1. And now we can actually have stimulated emission taking place. Light is being amplified. But this is not yet a laser. So optical amplifier is not a lasing device as such. It amplifies light, but it's not yet a full laser. And for a lasing action, we still need a feedback mechanism, and this is the kind of missing ingredient that we must now include in our description. So then what happens is that we are really actually amplifying very specific type of incident radiation. And this is the key thing why we want to add the feedback mechanism. So we just don't amplify any kinds of light, but very specific light that we wish. For example, the specific frequency of light with a given polarization and then in a given direction, so that we can actually have a highly directional light source. And because of this, the properties of lasers are quite different from, for example, compared to LEDs and flashlights. So this is the key, the feedback mechanism and the phase coherence. And subsequently, when we have a feedback, the coherence properties of light are even further improved, so that we can, for example, just have a very narrow band frequencies that are resonant inside a laser system, and then the coherence properties subsequently get improved. And how do we do this kind of feedback mechanism? So how do we realize this kind of back coupling? Is that we essentially put our laser crystal into and this is laser crystal is also known as the gain medium. So we put the laser crystal into an optical resonator, which is also known as a optical cavity. And more of these will be discussed in our section 8.6, where we will be introducing to you Fabry-Perot resonators. But until then, maybe we just imagine that we have 2 mirrors. We put the gain medium between the 2 mirrors, and then because of that, we may have a resonator. And now what this cavity does, this resonator does, at only very specific frequency components and directions are being amplified. So only light that oscillates at the very specific resonance frequencies associated with the properties of the resonators, only those are being amplified. And with the mirrors, we can also adjust that only in a given directions light is being amplified. So that these essentially are the considerations that we must think when we are thinking about laser cavities. More of these, of course, in our course on laser physics, that they will be speaking more about the laser cavities and the kind of types of mirrors and types of laser cavity configurations that exist, so that there are actually lots of engineering aspects into this question, but here we don't need to deal with those. And now I'm ready to show you essentially the main ingredients in one picture. So this is now a laser in action, and what are the main working principles underneath a laser. So we have a pumping of our gain medium, and that pumping could be done, for example, optically or electronically if we have a semiconductor laser. Then we have a gain medium in the middle of the cavity, and this is the medium that helps us to realize a population inversion. So it's really the electrons inside the gain medium that are being raised into a higher electronic state. And more importantly, with the pumping, we are raising them in such a way that the thermal equilibrium no longer holds, and there's actually more electrons in an excited state than electrons in the ground state. And this makes it possible that we can actually realize a population inversion, and when we have that, when we can actually amplify light. And now we place this gain medium between two mirrors and make a resonator, and then this resonator ensures that only specific frequency components and directions oscillate in a resonant manner inside the cavity, and then only those portions of light will be amplified, or components of light will be amplified. So only given frequencies of light will be amplified, and only in very specific directions. And this is different from a behavior of an optical amplifier. And then the other mirror is not perfectly reflecting, and then this ensures that small portion of light actually is being outputted here. So this is my so-called output coupler mirror, and its reflectivity is not 100%, but slightly less than this other mirror, and that ensures that the energy leaks out in a controllable manner out from the cavity. So a small portion of light forms actually the output, and most of the light actually will be inside the cavity. And this is how things work out. You have mirrors that form the Fabry-Perot resonator, and that's it. Now we have a laser device, and now we understand how we can actually generate bright, coherent sources by using these principles. So I thank you for listening this final lecture we had on chapter 5, and please join me quickly when we are discussing more of chapter 6 and chapter 7 and so forth. For example, in chapter 6 we will be speaking about propagation of light, if I remember it correctly, and then in chapter 7 superposition and so forth. But essentially now we know, after dealing with chapter 5, that how we can generate light, and now again in chapter 6 concerning propagation of light, we will be looking more into the details that how light propagates and is being reflected at the interfaces and refracted and so forth. So a lot of good stuff on the way. That was my main message at the end of this lecture. Please stay tuned. Lots of good stuff on the way. So I thank you for the patience, and I wish you a good day and a good week, and please join me when the time is right. Thanks and bye-bye.